So here we go. I'm going to do an example to show you the steps for writing the oxidation reduction reaction. So first of all, here's our example. We've got a single displacement reaction. So the first thing you're going to do is write the balanced equation. Now, in this case, since it's a single displacement reaction, we know that the aluminum is going to switch places with the zinc to form zinc as a metal and aluminum nitrate. Well, aluminum nitrate is going to, aluminum has a +3 charge, nitrate has a -1, so we need a subscript 3 for the nitrate, and that's aqueous. And then the zinc is going to be a solid. Okay, oh, I forgot to write this here. This is AQ. Okay, so here is our equation. We just need to balance it. So we've got a 3-2 combination here. So I'm going to put a 3 in front of the zinc nitrate and a 2 in front of the aluminum nitrate. And that gives me 6 of the nitrate groups on both sides. Now I need to put a 3 in front of the ZN and a 2 in front of the AL. So step 1 is complete. Complete balanced equation for this chemical reaction. The next thing we're going to do is we're going to write what's called the complete ionic equation. To do that, we're going to take all the aqueous compounds and split them up into their ions. All right, so I'm going to copy and paste the original reaction here. And now, instead of having this zinc nitrate as a compound, I'm going to break it up into its ions. Now, I have a subscript 2 with this ion, so and then there's a coefficient 3, so that means I have 6 of the nitrate ions all together. Now, because I'm writing it as an ion, I need to put in the, oh shoot, what did I do? Because it's a, sorry about that. There we go. We need to put a -1 charge there. Okay, and then we have 3 of the zinc ions, and that has a +2 charge. Okay, so what I've done here is I've taken that zinc nitrate aqueous compound, and I've represented it using its ions. I can go ahead and put an AQ in there with the ion. I'm going to do the same thing with the aluminum nitrate. I'm going to break this up into its ions, and again, I've got 6 of the nitrate ions. I'm going to take out the subscript here because we're actually breaking it down into its ions. It's got a -1 charge. So there's 6 of those, and we have 2 aluminums, and that has a +3 charge. Okay, so the complete ionic equation is really just the same as the balanced equation, except I have broken up the ionic compounds that are dissolved in water and represented them as ions. Okay, the next step, write the net ionic equation. Well, I'm going to copy what I have from step 2, and I'm going to paste it here. This step is really easy. The net ionic equation, we're going to simply remove the ions that are identical on both sides. So if you look over this reaction, you'll notice that there's 6 nitrate ions as a reactant and 6 nitrate ions and in the product side. So I'm going to literally just delete those. There they go. Goodbye. And I'm going to take away this one. And what's left is what we call the net ionic equation. Those ions that are the same on both sides are called spectator ions, and they don't participate in the reaction, so goodbye. We can do without you. The net ionic equation just shows what's happening in the chemical reaction. Okay, so we're making progress. Now I'm going to split this into 2 half reactions. One of the half reactions is going to show what's happening to the aluminum. The other half reaction is only going to show what's happening to the zinc. So let's start with the aluminum. All right, so I know I have these 2 aluminums. Oops. Well, actually, you know what? I'm going to work with it just like that. I can get rid of everything except the aluminums. There we go. There we go. There's my half reaction for aluminum, and I'm going to do the same thing with the zinc. Now, I'm keeping the coefficients in there because we need to know, because these 2 reactions are happening together. And the coefficients are important because they help us figure out the number of electrons transferred. Okay, so our half reactions are almost complete. The only problem is the charge. Now, if you look at the first one, aluminum goes from a neutral element with a charge of 0 to a +3 charge. So essentially, on the product side, we have a total of a +6 charge. And what that means is that the other, to balance the charge, we have to put in 6 electrons. Electrons are represented with an E with a -1 charge. All right, now, not only does that balance out the charge, because the charge on both sides of the reaction has to be equal, but also it does a good job of representing what happens to an aluminum when it goes from neutral to +3. Every time it goes to a +3, it has to lose electrons to become positive. Now we're going to do the same thing here. Notice that in this reaction, the electrons have to go on the reactant side. 6 electrons here. All right, so the net transfer is 6 electrons. The top reaction, 6 electrons are lost. In the bottom reaction with the zinc, 6 electrons are gained. And that's what makes it an oxidation reduction. Now what we're going to do is identify which half reaction is the oxidation and which one is the reduction. Well, Leo, my favorite phrase, Leo Ger, loss of electrons is oxidation. So the one that's losing electrons would be the top one. So this is our oxidation half reaction. And the one that is gaining electrons, why did that happen? Is the second one, because the zinc is gaining electrons. So this is our reduction. Okay, so there we have it. So we now know what's happening to the aluminum, what's happening to the zinc, which one's the oxidation, and which one's the reduction, and we also know how many electrons are transferred in this reaction.